Let's look at the corresponding magnetic case, the magnetic field. Magnetic field, and let's look at the linear term first, which is this one. And I think in the textbook that Hamiltonian is then called like this, with the Greek letter xi. So what is that? That is E divided by ME, sum over all electrons, I, the vector potential at the position of the electron, scalar product with the canonical momentum of the electron. Now if I insert the expression for the vector potential of a static and homogeneous magnetic field, which is this one here, what do I get that? Then I guess I get E divided by 2 ME again, sum over all I. And then in the first place I get B cross Ri, position vector of the electron, minus this gauge origin vector, dot product with the canonical momentum operator. Now, this is sort of, this is cross product times the dot product, sort of it's one of the possible triple products of vectors. And there's a rule that you can cyclic permute them. So you can, that being scalar and cross product, you can cycle around. But you have to be careful. If you just have the normal classical A cross B dot C sort of expression, you can sort of just cycle them around. So this is the same as C cross A dot B, the same as B cross C dot A, like this. But you have to be really careful if you do that here, because this is this gradient operator. So you can't just put if you put the gradient operator here, then suddenly you take the gradient of everything which is behind, and that wasn't the case here. So you have to write that cycling around, you have to write in a different way. In particular, and the version we want is, we want to have basically those two switched. So if you do it properly, you can get it to be E divided by 2 ME, sum over all electrons. And now we get Ri minus this gauge origin cross Pi, like this. And we better put a parenthesis around it. And then I can have sum over I, and then the vector potential, the magnetic field in front of it. So that, well, the vector potential is not, the gradient operator is not going to act on it, but it doesn't matter, I could put it behind because the magnetic field is a constant field here, so it doesn't depend on position in space. So and here I could put it behind, but it's better put in front. Now, what is this? Do I miss a minus sign? No. What is this here? R cross P. R cross P. That's the angular momentum of electron I. So it's the angular momentum operator, R cross B. So we have the angular momentum operator in here. So I could write that now as E divided by 2 ME sum over I B cross Li, like this, in the first place. And I better sort of indicate that there's this gauge origin. It's not, it's relative to this gauge origin. Now, like here, we know that the energy of a moment in a field is minus the moment times the field. And we also, or at least I said that the same holds for a magnetic moment in a magnetic field. So this, of course, should be minus the magnetic moment operator of the molecule, or the electrons, times the external field, which then implies that the magnetic moment operator is that minus, which is not there, so it's minus E divided by 2 ME sum over all electrons, and then the angular momentum operator. And that is precisely, I mean, that is also the classical expression for the magnetic moment of a charge moving around, a charge having an angular momentum. So again, in a way, we ended up with something we ought to have known before. If you have orbital motion of electrons moving around in a molecule, they have angular momentum. There's in principle a magnetic moment for that, and at least I can write, and this will interact with the magnetic field. So that's a linear term.